Hey, welcome back to Algebra, describing systems and predicting. And this is part 2, where we're going to build on what we've just been doing. And let's have a look around the screen. Here's an old one over on the right here. There's a little system there where we were trying to create a quadrilateral within a given square that we had a piece of paper, if you remember, back to the earlier presentations. And we wanted to look at what sort of areas that particular system of division of that square piece of paper provided. And then we've recently done this one over here, where we took an A4 sheet and started folding it, and what did that folding system produce as a family? I don't know, it depends on the number of folds, doesn't it? The number of folds generated, there's an interesting word coming back again, generated a different number of valleys and mountains and so on. And there's a few other examples of systems. There's a system of numbers, of shapes. Here's another shape one. Here's some more numbers. So I'd encourage you to try to develop a way of thinking which enables you to analyse or describe the system, and then we want to try and predict what's going to happen if we continue that pattern on. Could be quite useful, couldn't it, in everyday life to see what's happening there. So let's go down and have a look at some of that. Here we go. This is what we want to do now, using algebra to describe a system and predict. So first of all, we're going to ask the question, when we look, as we did at that paper folding set of data, when you fold the paper, can you see a pattern in the number of valleys, the number of mountains, the number of total folds, for example? And we just left that in part 1 of the describing systems. And then, can we use maths, or algebra in particular, to describe that pattern? What's going on there? And then, if we're happy with our description, can we then predict what might happen, if that's practical, not assuming too much, looking at the limitations, perhaps, of the system? Can we then predict what the patterns might lead to for a bigger and bigger example, extending the system? Okay, well, let's have a look now at some of these that I put up on that first screen. Can you see a pattern? Can we use maths or algebra to describe it? Can we then predict? Is that realistic? Well, let's look at these numbers. Everybody's sort of going to see different patterns here for a start. I don't know, let's go with one that perhaps is the most obvious. What do you do to 22 to get 44? Times it by 2. And if you times it by 3, you get 66. If you times it by 4, you get 88. So maybe that's the thing that's going on, they've got in common. They're all multiples, so you see, I see a pattern. They're all multiples, if you like, of 22 is one way of doing it. And then could we use, well, that's a mathematical statement, but could we use algebra? So we could say any term, call it Tn, the nth term here, this would be the first term, so n would be 1, the second term, the third term, and so on. So any term, how do you get it? Then you multiply, it's n lots of 22. You multiply 22 by the number of the term. So the first term is 1 lot of 22. The second term is 2 lots, 3 lots, 4 lots. So there is an interesting system that we've described, and we could predict what would be the 100th term. If we went out 100 times, it'd be 100 times 22. How powerful is that? Okay, we don't have to put all the terms in between. We can go like straight out to that 100th term. That's powerful stuff. Is there another pattern you can see? Generally with systems, there's probably more than one way of describing them. Let's try and do this differently. This time I'll rewrite it down here so I don't mess up the diagram there, so you can look back at it. So here we could say this is going up by 22, by this, 22. Okay, so they are multiples of 22. And the next one if we added another 22 would be what? 22 onto this is 110. Okay, so you could think of it as adding on another 22 rather than multiples. So it would give you the same thing. At the end you would have n lots of 22s. Okay, so you could think of it this time as any term is you've got 22 plus, now the second term has got one 22 added on. The third term has got two 22s. So the number of 22s added here is one less than the number of the term. So by the time you get to the fourth term, how many 22s have you added? Because this time you're not starting with the first one. You're saying I've added 3 22s to get to the fourth term. We'll still come to the same number there, but a different way of thinking. So what is important? What is ways of thinking? Okay, they're important in maths, and to look at it in as many different ways as you can, to look at the things that are the same in the system and things that are different. Way back to where we looked at families. Oh, how's it going? You're getting your head around that? Gets a bit complicated, doesn't it? Come down now, and I want you to try and do this one. So pause the presentation and see if you can add, 2 or 3 more shapes to make a family for this particular system. You need to look at it carefully. So pause the presentation and have a go. All right, let's have a look now. What's going on here? Let's try to recognise the pattern. You start with a triangle. You then add one to its side to make a rhombus shape, isn't it? A rhombus shape. This looks like an equilateral triangle here. And then you put another one there. A rhombus is a parallelogram with 4 sides equal. That seems to be what we're doing here. And then when you get to there, you bring this one down to complete the triangle. And then there's a gap here, and you make up your end rhombus, if you like. The whole thing's not a rhombus anymore, but just you make up a rhombus through that. And then you're going to bring this down again, aren't you? So we've got here this, and this from there, and you're going to bring it down. So that'd be your next one, and the next one is getting hard to write this now. Is this, hang on, and we just go here somewhere like that, and then we've got this down here. So we're going to have to complete that end rhombus there. So you can see the idea here, building up by addition of a triangle and then completing it into a rhombus on the end. All right, so that's an interesting pattern. How would you describe that mathematically? Well, you would say you, add a triangle each time, and it comes in 2 types, I suppose. One where you extend it down, so like this one, extending it down to the baseline, or one where you complete a rhombus. First one that you put down is extend to base, and then the second one after that is to complete a little rhombus on the end of the shape, if you like, if you're trying to describe what's going on there. It's important to make some sort of attempt at that description. And of course, we would say if n is 1, the first term, there is 1 triangle. When n is 2, there are 2 triangles. So that's this. This is the first one. Call it n equals 1. This is n equals 2. n equals 3. So the number of triangles you end up with right out at the 6th one, 6 shape, is 6 triangles. 1, 2, 3, 4, 5, 6. Are you getting the idea of using maths and algebra to describe a system? And we could predict out here what the 10th one would look like. Are you noticing that with the even ones, here n is 4, the rhombus on the end is completed. So we would predict at n is 10 that there would be 10 triangles and it would end up like this. Okay, dot, 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 dot. But it would be a complete rhombus because here all the even ones are completed on the end. See, this is not. This is n equals 5 and it hasn't got that closed rhombus on the end. So there's some interesting mathematical analysis going on there. Okay? All right, so let's go down. I'll give you another one to play with here. And here's a number 1. I want you to pause the presentation and see what you can do with this now. All right, let's have a look. A bit of a hard one. What do you do to 2 to get 5? 5 to get 10? A bit hard to see. Maybe we could put in 2 going to 5, you have to add 3. 5 going to 10, you have to add 5. 10 going to 17, you have to add 7. 17 going to 26, you add 9. 26 going to 37, you add 11. 37 going to 50, you add 13. Ooh, so although the numbers directly didn't show us much, we can see their connections between each other. This is called a recursion formula, where you connect each term to the one that came before. Okay, so what is the pattern here? Well, Tn, the nth term, so this is when n is 1, the first one, when n is 2, when n is 3. So what is it? It's the one before, the term before, plus, it's all odd numbers that you're adding here. So what is it? When you are coming to the third term, it is 5 that you have to add on to the preceding one. And when you come to the fourth term, it is the 7 that you have to add on. So you've got to add on the odd integer which fits in that spot. So if you start with the first odd integer is 1 down here, the second odd integer is what you add to get to the second one, the third odd integer is 5, the fourth odd integer is 7. So the odd integer, which one? Well, equal to the nth odd integer. So if you're at, let's take this term here, that's n is 6. So here the 6th term will be the 5th term plus the 5th odd integer. What is that? So the 5th term is 26 and the 5th odd integer, 1, 2, 3, 4, 5. Whoops, made a mistake there, haven't I? We want the 5, 6 odd integer, that's right. Okay, so that is correct. Adding on 11 to 26, the 5th odd integer. Yep. So getting complicated, isn't it? So that recursion formula says you take any particular term and add on the nth odd integer after that. Hard stuff. Okay, how are you going? Are you trying to develop ways of thinking here? What about another diagram type? I want you to pause the presentation and have a go at this one. Well, what are we doing here? How would you describe it? Try and describe the pattern. So I reckon what I see, apart from this one, I see a right angle triangle with dots here and here. Okay, and they all seem to be right angle triangles. And what's happening in our pattern? Well, this has gone out to having one more there. This has gone out to having one more, and the end has grown by 1. See the way of thinking here, this analysis that we're doing, trying to describe the pattern. And I've run out of room here, but we'll do it down here, which is not good. So we've extended this line out by 1 to 4, and extended this one out by 1 to 5. Okay, so 4 as well it should be. 4 and 4, sorry, so we should be there. Extended both of them out. Okay, and now we're going to join those. So this has another one in here. Oh, hang on, another one in here. We've got to get the scale right here. And this has, I've gone off the scale. This has another one in here. So we've got, I think I've still got it wrong. I've drawn this one. I should have drawn the next biggest one up. Okay. Well, no, not yet. We'll stay with this one. So I've said that's what you're doing. So what's the next biggest one up? Here we got this. 1, 2, 3, 4, and we'll just get rid of that, and we'll make a 5 there. And up here, 2, 3, 4, 5. So it's gone 1 up in both ways. You can see the pattern. We're increasing the height and the width here, each by 1 each time. And so then coming across here, there'll be 3, 4, and here there'll be 3, and here there'll be 2. So here we have got that. And the next one would be 6. Increase it to there, and 6. Increase it across to 6 there. Okay, and then of course this one's got 5. This one's got 4. And this one's got 3. This one's got 2. Oops. 2 including them. Okay, so then we have this one here. And you could look at the number of dots and see if that forms a pattern. 1 dot, 3 dots, 6 dots. What have we got here? Add them up there. 10 dots. And then what are we up to? We're up to this one, I think. We've got 5, 9, 12, 15 dots. And on this one, 6, 11, 15, 18, 21 dots. So there's a sequence of dots if you want to look at that. That's interesting, because what are you noticing? We had 2 dots, then we had 3 dots, 4 dots, 5 dots. Why is it growing by an increasing number of dots? Can you reason that out here? By looking at when you increase this by 1, it's got a bigger and bigger effect, hasn't it? In there, as you push the base and the height of the right angle triangle out. All right, how's your what's going? Your ways of thinking? How's that going? Getting a headache yet? Well, I've got more for you yet, so come on down and let's have a look at this one. 1, 2, 4. This is a rather special case because the numbers are so simple, aren't they? There's a few different ways you could look at this one. I don't know, what do you see first? I don't know, we'll do it this way first. 1 increases by 1 to 2. 2 increases by 2 to 4. So we could have a pattern where this increases by 3 to 7. And then add 4, it increases to 11. Add 5, it would give you 16. So that would be one possible pattern there, where we're adding bigger and bigger, one more integer as the difference to each of the terms there. What's another way? 1, 2, 4. Well, you could think these are being multiplied by 2. So they're actually powers of 2. 8 multiplied by 2, 16, 32. It could be either of those. There's no absolutely correct answer here. We're just looking at the system in terms of different patterns with a limited starting point. We've only got 3 terms there to start with. So with this one, what would be the algebraic statement? Well, this would be 2 to the 1 2 squared is 4, 2 cubed, and this is, you might not know this yet, 2 to the naught. So the term there using this one would be get 2 and raise it to what power? Well, the second term has power of 1. The third term has a power of 2. The fourth term has a power of 3. So it's n take 1, isn't it? You have 2 raised to the position of the term less 1. So out here, what term is this? This is the sixth one. N is 6. So it should be 2 to the 6 take 1 is 5, which is 32, which works. So your work with powers, as we touched upon last time, might not be strong yet, but we can get the idea. Just remember the definition of that. 2 to the 5th means 2 multiplied by itself, so you've got 5 2's in a row, which would come to 32. Got the idea there? Okay, how are you going? A little bit more, not much to go now, but we're trying to get ways of thinking. What's W-O, no double eight, W-H, what's W-O-T, ways of thinking. Okay, what about this? You could play around with this for a while. Pause the presentation and see if you can work out what system might be represented by these letters. Okay, well, I think we'll just do one here. You might talk to classmates and your teachers about other possibilities. This could be Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, something like that. And then it would repeat, Sunday, Monday. That could be the system that we're talking about there and trying to describe it. Are there any more using those letters? Have a think about that. Let's go to the last one now and have a look there. No, I don't think this is the last one, actually. I think there's one more. All right, 314159. Pause the presentation and think about it. Maybe discuss it with your teacher and your classmates and see if you can describe the system here that might be happening with these numbers. All right, let's have a look. If we're trying to do it with numbers, I don't know what you can see. We're going 3 to 1, 4 to 1, 5. So this is 3, 4, 5. So maybe 5 to 9 and then 7 to 9. Repeating this idea. The 1 you could think of as 10 and then you're going to 9. And this is 3 to 1, 4 to 1, 5 to the next number, if you like, that you're going to put in there, then 7 back to that number. Yeah, we're struggling a bit with the pattern there, I think. But there are other possibilities you might look at. And also, the interesting thing about this is that decimal there, we put a decimal point between the first two, is, and if it keeps going, it's equivalent to pi. Remember, circumference of a circle is pi times the diameter, or the ratio of the circumference to the diameter of a circle is the value of pi. And it's a non-terminating, non-recurring decimal, it just keeps going. So maybe that sequence of numbers is meant to represent pi. Are there any others? Have a think about it. Okay, we'll finish off. Got one more here. 31, 28, 31, 30, 31. Couple of ways you could look at this. There probably are more. So think about it. Get ways of thinking happening in the whole class. I want you to pause the presentation and see what you think. All right, well, I don't know. What have we got? 31, then we went to 28, then back to 31, then we went to 30, then 31. So you could think of 31 as sort of punctuation marks, and it goes 28 to 30, maybe then to 32, back to 31, and then what would you do? 34. Can you see what I'm doing? Saying that these in between the 31s are increasing by 2, and the 31s are sort of punctuation marks. There's lots of different ways that you could think of this as a system. That would be one of them. Bit doubtful, unless we know what it's representing. We're guessing a bit, aren't we? Or you could say 31, 28, 31, 30, 31 are the days in the month of January, February, March, April, May. The next one would be June, July, August, September. These are the days in the month then. Maybe it's that system that we're trying to summarise. So can you see that we need to develop ways of thinking about sets and systems of numbers and other shapes and things, so that we might be able to analyse it and then go on and possibly, if it's practical, to predict. Just remember from part 1 of this little set of presentations, we found you can't always extrapolate. You can't always keep going along here without knowing what the system is and whether it could continue. All right, I hope you haven't got too much of a headache. In the next presentation, we're going to practice some mathematical ways of looking at trying to work with systems of numbers and describing them, particularly with numbers, not so much with shapes. But for the moment, it's cheers from me.